there's one name in science that stands out beyond any other, it's Isaac Newton. His ideas, theories, and inventions without a doubt revolutionized the way people thought of classical mechanics, optics, calculus, and the universe as a whole. But what if his ideas were wrong? What if the very foundation of physics that Newton handcrafted was inaccurate? Nah, I'm kidding. Newton isn't wrong, at least not for the most part. Well, obviously we don't know if he's completely right or completely wrong, because our scientific instruments aren't exact enough to know. But the science community generally agrees that his formulas, most of his formulas, are relatively accurate. Wait, say that again. Most of his formulas are relatively accurate. Relatively. Relative. Relativity. That's what it all comes down to. Einstein's theory of relativity. In their most fundamental interpretations, the two theories of relativity redefine the whole idea of motion. Of course, they can get much more complicated as well, especially with the ideas of the speed of light and spacetime. But together, the special theory of relativity and the general theory of relativity are the foundations of modern physics. The main difference between them is that special relativity deals with non-accelerating motion, meaning that the object in question is either at rest or moving at a constant speed, while general relativity deals with accelerating motion that causes the object to either change speed or move in a curved path. We'll start with special relativity because it provides a solid foundation upon which general relativity builds. Einstein's special relativity theory was based on two major concepts. First, that the speed of light is a constant, and nothing can go faster than that. And second, Galileo's principle of relativity. Basically, all it said was that the laws of physics are the same for any observer in any condition. By combining those two ideas, Einstein came to the conclusion that the speed of light is independent to the observer. In other words, the speed of light is absolute and does not need another object to be relative to in order to be measured. For an example of what is relative to something else, just look at this clip. There are no objects in the view to be relative to, so you can't really tell if you're moving or not. When you add objects to the view, all of a sudden you can tell that either you or the objects are moving. The speed of light is not like this. It doesn't need anything else to be relative to in order to be measured. This special characteristic caused Einstein to believe that it served as the cosmic speed limit. This revelation causes more questions, however. If I'm in a spaceship traveling at 250,000 kilometers per second, and I shoot a laser at the speed of light, which is 300,000 kilometers per second, does that mean that the light is only traveling 50,000 kilometers per second faster than I am? Or are the two numbers added to create 550,000 kilometers per second, a speed that is faster than the speed of light? The answer that Einstein, the great physicist, created was that it travels at neither speeds. I would still measure the light to travel at the speed of light, but in reality, the light is causing space to contract and time to dilate. The distance that light is traveling is being reduced, and the time it takes is elongating. When you think of the formula, speed equals distance over time, then for the speed to remain the same, the speed of light, the rate at which the distance reduces must be a factor of the rate at which time elongates. Einstein's idea allows for there to be no violation in the actual laws of physics. It just manipulates the very foundation of speed and shows a key relationship between space and time. That's all there is to the special theory of relativity. As the velocity of an object increases, the distance it travels will reduce, and the time it takes to travel that distance will increase. At the speed of light, the distance traveled will go to zero, and the time it takes will be infinite. Why is that true? Well, it's by the equation E equals mc squared, which I'm pretty sure you've heard of. Imagine this scenario. When you push an object faster and faster, it seems to become heavier and heavier, and you apply more force to it. The energy that you're forcing into the object is being turned into mass, because the energy can't just disappear. It must change form, and in this case, it's turning into mass. Einstein realized that an object being pushed at the speed of light would have infinite mass, which is impossible to push. That's why an object can't actually travel at the speed of light. Another child of the special theory of relativity was the idea of spacetime, which is hugely important to the general theory. Einstein realized that the concept of now is completely trivial. Light, as fast as it is, still takes some time to travel from place to place. Therefore, anything that we see has to be from the past, even if by the smallest of margins. Einstein believed that the past and future are already written out on a fabric of spacetime, a four-dimensional material stretching across space. Due to the fact that space can be contracted and time dilated, Einstein couldn't rely on those individual things for observation. Spacetime together, however, could not be manipulated, and therefore served as the only thing other than the speed of light itself that was absolute in the universe. Want to hear something crazy? Well, here you go. Gravity is acceleration. That's what part of the general theory of relativity says. Let me explain. Isaac Newton, our forgotten physicist, believed that objects have this natural pull between each other because of their mass, but he didn't know where this pull came from. Einstein took it on himself to find the truth behind gravity. During his investigation, Einstein realized that if a person was standing in a spaceship that was accelerating 9.8 meters per second squared in space, and they dropped a weight toward the ground, the weight would fall directly to the ground just like as if they were on Earth. Using this result, Einstein knew that it was not mass that mattered for gravity, it was acceleration. Now imagine that same astronaut pointing a flashlight across his spaceship. The light will curve slightly downwards as it travels across the room. But I thought light travels in the shortest distance possible between 2 points. Why would it curve or bend if it isn't the shortest distance? The answer, which Einstein proposed, was that space itself was curved. On a curved surface, the shortest distance between 2 points is actually a curve, or a geodesic, as anyone who has traveled on an airplane would know. When Einstein combined the idea of gravity being the same thing as acceleration with the idea of a curved space, he realized that gravity, or acceleration, is caused by the curvature of the fabric of spacetime. Just as the visual shows, the smaller ball is slowly circling around the larger ball because of the size of the depression. You can reenact this exact scenario on a trampoline. If there's a bowling ball in the center, then there's an obvious depression in the middle of the surface. If you shoot a marble around the edge of the trampoline, it will slowly circle around, following the depression. This is what Einstein believed was the image of space. The fabric of spacetime served as the trampoline, the bowling ball in the center was the sun, and the marble is a planet. And that is what the general theory of relativity is. The fabric of spacetime is curved by the presence of masses or energies, which in turn affects the masses and energies of other objects on the fabric, and that phenomenon is what we know as gravity. While it might sound completely unreal and science fiction-like, I tell you this. The scientific community has observed several scenarios where the planets are getting closer to their suns. Our solar system is slightly special, as the speed of the rotation of the planets is so great, such that they're not getting drawn towards the sun. However, that's not to say that the general theory doesn't have a bearing on our solar system. Newton's laws, when applied to the orbit of Mercury, failed to accurately predict the path because the planet had some strange orbital paths. However, Einstein's theory of a curved spacetime was successfully able to predict the exact path. And that, in a nutshell, are what the theories of relativity are. In a quick recap, special relativity is the idea that as speed increases, space contracts and time dilates, and that led to the legendary equation E equals mc squared. General relativity explains the idea of curved spacetime and the redefined concept of gravity, and that led to the prediction of black holes, time travel, parallel universes, and so much more. While I covered a lot in this video, if you would like to read more, I have prepared a website detailing Einstein's life, his theories, and his legacy. It can be found at this URL, and the link will be in the description as well. Be sure to check it out. Thank you all for watching.